In the name of Allah, the most gracious, the most merciful. All praise is due to Allah, and peace and blessings be upon the messenger of Allah, our master Muhammad, and upon his family and companions altogether. Now as for what follows, by time indeed mankind is in loss, except for those who have believed and done righteous deeds and advised one another to truth and advised one another to patience. Let's understand the distribution. Each contains, as it disconnects due to a fault, no voltage feed from the other side. If feeding from both ends, place 2 breakers. This box has a CT, relay, and breaker. If a fault at point 1 breaker, next to bus bar R disconnects. If fault between points, breaker next to bus bar disconnects. For example, the relay at cannot distinguish between faults at, as the measured value is the same. If there is a fault in the distance between the 2 points, the circuit breaker next to the bus bar must be disconnected. Likewise, if there is a fault in the distance between the circuit breaker next to the bus bar must be disconnected. These can't tell if the fault is on its protected line or on the distant or adjacent line. The relay at can't tell the fault at, because they are close and impedance is similar. Opening the circuit breaker at bus bar H in the event of a fault at point number 1 is incorrect, and the reason is I lost the load at bus bar R unnecessarily. Help this relay by using relay time grading margin or communication channels between substations, because they are close and impedance is similar. Opening the circuit breaker at bus bar H in the event of a fault at point number 1 is incorrect. The reason is I lost the load at bus bar R unnecessarily. We assist the overcurrent relay. The delay lets the nearest relay disconnect first. If R fails, relay H disconnects next. Or by using communication channels between the local substation and the remote end substation, the time delay will allow the relay closest to the fault to disconnect first. If the fault occurs at point 1, then relay R should disconnect. If it trips for any reason and relay R does not respond, then relay H should disconnect. Thus, this time delay that we added allowed relay R to disconnect before relay H. This technique is what we call coordination or selectivity, which is poisoned to give less separation time for nearby faults and longer time for distant faults. Now, relay edge will make a time delay if the fault occurs at 2 points, either point 1 or point 2. If the fault occurs at point number 1, I have no issue with the time delay, because it will establish coordination between H and R. But if the fault occurs on my line, which is at point 2, what's the need for the time delay? I mean, a fault happened within my protection zone, and there's not even a 1% chance that another relay will operate to isolate the fault, so why should I wait for this time delay? Subscribe channel. So the solution here is to use communication schemes to determine the location of the fault, whether it's an internal fault or an external fault. This means it's either within my protection zone, within the area I'm protecting, or it's an external fault outside my protection area. These schemes will be explained later. We coordinate timing using the definite or inverse time curve. If a fault occurs at point 1, relay R trips first, then relay H and relay G. Time coordination typically starts from the load to the source side or vice versa. From the load side, we use instantaneous or definite time over current since no coordination is needed, thus no delay. Relay H coordinates with relay R and relay G with relay H. Relay R has no. We usually start the time coordination from the load side to the source side. When we start the time coordination from the load side, we use instantaneous overcurrent or definite time overcurrent. Relay H coordinates with the relay to its right. Relay G coordinates with the relay to its right, and there is no relay to the right of relay R. If we use the definite time curve with all the relays, we notice that it is characterized by the operating time for each relay individually. Large faults close to the source require a long time to disconnect. Relay G coordinates with the relay to its right, and there is no relay to the right of relay R. Thus, apply instantaneous or definite time overcurrent on this relay. Using the definite time curve with relays R, H, and G, coordination shows each relay's operating time is independent of voltage. However, large faults near the source take longer to disconnect. Thus, it is not preferred, especially for a radial feeder. Conversely, using inverse time characteristic, faults near the relay trip faster. Unfortunately, varying conditions from max to min load cause significant disconnection time changes. This arrangement has advantages and challenges. Voltage level doesn't matter, but large faults near the source take time to disconnect, making this setup less ideal for radial feeders. Relay timing with inverse time. Characteristic allows faster. This arrangement is not preferred. Coordinating relay timing with the inverse time characteristic allows faster tripping for faults near the relay. However, varying conditions cause significant disconnection time variation. It's common in electrical systems. Short lines have similar impedance at both ends. In such cases, the definite time curve is preferred over the inverse time curve. We use the definite time curve when there's no coordination with other protections or when fault current differences are small. The normal inverse curve suits long lines. It can provide a long disconnection time for distant faults remotely, but it is widely used in electrical systems. For short lines, impedance difference is minimal. Definite time curve is preferred over inverse. Use definite time curve without coordination or when fault current difference is small. Normal inverse curve is preferred for long lines with smaller end fault current. Used in long lines and high current restoration cases, the disconnection time is also considered to be close. So in this case, it's preferable to use the definite time curve more than the inverse time curve. Therefore, we use the definite time curve when there is no coordination with other protections or relays in the network, or when the difference in the fault current values for nearby and distant faults is small. On the other hand, the normal inverse curve is preferred for long lines. So, when the fault current value at the end of the line is much smaller than at the beginning, it is used in long lines, as well as in cases that result in high current when restoring service, such as motor starting current or transformer inrush current. What should we know about the occurrence of inrush? The occurrence of inrush in the motor is sometimes referred to as starting occurrence or locked rotor occurrence, and this will be detected when we start pushing or need some time. Motor starting current or transformer inrush current.
What should we know about the occurrence of inrush? The occurrence of inrush in the motor is sometimes referred to as starting occurrence or locked rotor occurrence, and this will be detected when we start pushing or need some time. It's also important for us to know how to do this so we can improve the motor's performance. So here we have the inrush current of our motor, which is 2.4 amps. So what do you expect to see through the inrush current? Well, to take the inrush current, I will disconnect the motor to the amp, and I will need a motor switch that distinguishes inrush. Press the inrush button. Then when motor starts, you need to do an inrush test. I'm doing an inrush test. Then when my motor starts, I hit the inrush button. There are no known scientific methods to determine the ideal curve shape for each case, but what has been mentioned is what is actually used in practice and in the job market. Motor current is crucial.
There are known scientific methods to determine the ideal curve shape for each case. But what has been mentioned is what is used on the ground and in the labor market. Set instantaneous overcurrent for high current fault, trips instantly when fault current exceeds setting current, no delay, timing coordination between relays is a drawback, especially with short similar length series lines, considerations needed when setting relay. For series lines, set pickup value to trip above 125% of symmetrical fault current at next station, for example. There is no time delay in it, and we said that the drawback of the instantaneous overhead relay is the difficulty of time coordination between the different relays, especially if there are two short lines in length and in succession. Therefore, we need to take several considerations into account when calculating the setting for the instantaneous overcurrent relay. If the device is used to protect series lines, the instantaneous overcurrent pickup value should be set to trip at a value higher than 125% of the symmetrical fault current at the next station. For example, when setting up device B, we first need to determine the maximum fault current at bus bar A, and then we set the instantaneous tripping unit of device B to a value higher than that at bus bar A by a range of 20 to 50%. We usually take 125%. Cut at the next stop. To set up device B, find max fault current at bus bar A. Set device B tripping unit 20-50% higher than bus bar A. For the last uncoordinated device, trip value above half short circuit current. Set pickup value for instantaneous overcurrent. 3 breakers per section. Max short circuit at bus bar C is 3 kA, lower than bus bar A's 7 kA. Set pickup current for relays B and A. As for the last device, set instantaneous trip value above half short circuit value. Start setting steps farthest from source. Move towards it. We have 3 circuit breakers per section. Max short circuit at bus bar C is 3 kA, lower than 7 kA at bus bar A. Set pickup current for relay B and A for instantaneous overcurrent. Notice that the maximum short circuit value at bus bar C is 3 kiloamperes, which is lower than the short circuit value at bus bar A, which is 7 kiloamperes. This is due to the impedance value, as we mentioned before, where the farther the fault is from the source, the lower its value becomes due to the increased impedance that the relay sees. Now we want to set the pickup current value for relay B and relay A. Instantaneous overcurrent for relay B and relay A. To set the pickup current for instantaneous overcurrent on device B, determine the max fault current at bus bar C. Set device B to trip at 120% of this max current. With a max short circuit current of 3 kiloamperes, relay B is set at 3.6 kiloamperes. For relay A, calculate the max fault current at bus bar B, setting relay A at 4.8 kiloamperes, which is 120% of 4 kiloamperes. From the maximum company police, which is on the instantaneous overcurrent for relay B is set at 1.2 times 3 kiloamperes, making the instantaneous overcurrent for relay B 3.6 kiloamperes. To set the instantaneous overcurrent on relay A, we calculate the maximum fault current at bus bar B, so relay A is set at 120% of 4 kiloamperes, which equals 4.8 kiloamperes. For the last uncoordinated device, the instantaneous overcurrent value should be set to a value higher than half of the short circuit current passing through it. This coordination avoids device B tripping instantly due to a fault in front of C and prevents relay A from tripping due to a fault in front of B, and so on. Kiloamperes. As for the last device that does not coordinate with anyone, the instantaneous overcurrent value should be set to a value higher than half of the short circuit current passing through it. The goal of this coordination is to avoid having device B trip instantly due to a fault in front of C, and likewise to prevent relay A from tripping due to a fault in front of B, and so on. Regarding the additional 20% to 50% margin, it was chosen to avoid having relay B trip instantly due to a fault in front of relay A, as it is known that there are chances of error in determining the current value due to control devices or others, for example. However, the total of these errors is usually less than 20% of the fault current value, which is why this margin was selected. This margin can increase to 50% if the instantaneous overcurrent is used on the primary side of the power transformer, in order to avoid any potential incorrect tripping, especially after adding a new element, which is the current of the... However, the total of these errors is usually less than 20% of the fault current value, which is why this percentage was chosen. This percentage can increase to 50% if the instantaneous overcurrent is used on the primary side of the power transformer in order to avoid any potential incorrect tripping, especially after adding a new element, which is the current of the... To avoid any potential incorrect tripping, especially after adding a new element, which is the current of the... So, the potential error margin is raised to 50% instead of 20%. On the primary side, the potential error margin is raised to 50% instead of 20%. Inspiring the renaissance of the nation. Dealing with transformer inrush current is significantly different from dealing with cold inrush current. So what is the difference between them? Transformer inrush current only appears when starting the transformer, and its values can reach 5 or 6 times the normal current, or even up to 20 times the normal current, depending on the transformer's capacity. However, this is not the core of the problem, especially since inrush current lasts only a second or slightly more, and its value can decrease during this brief period. But the major issue is that this inrush current only flows in the power transformer and does not flow in... It flows in what is called the transformer magnetizing circuit. The value can decrease, but the inrush current flows in the transformer magnetizing circuit, not the power transformer. This can trigger overcurrent protection, tripping the transformer, though it's natural. Disable protection until the transformer is operational and the inrush current subsides, then re-enable it. Inrush current can trip transformers. Inrush current in transformers can trigger overcurrent protection, mistakenly causing a trip. To prevent this, one method is to temporarily disable protection until the transformer is fully operational. A safer approach is to reduce the sensitivity of the protective device. A widely used method is the second harmonic block. This method distinguishes inrush from fault current by analyzing the second harmonic content. High levels indicate inrush, while low levels suggest a fault. This simple solution is dangerous because a fault could occur when energizing the transformer, leading to its destruction without protection. Incorrect tripping during inrush current can be avoided by reducing the protective device's sensitivity, raising its settings. A common method is using the second harmonic block, chosen because inrush current is rich in second harmonic. Thus, inrush current can be distinguished from fault current. High second harmonic indicates inrush, low indicates fault. When the transformer starts, the relay analyzes the current. If it contains high second harmonic, over 20% of the setting, it blocks itself. If lower, it allows tripping, especially with cold inrush. The reason for choosing the second harmonic block is that when analyzing the inrush current, it was found to be rich in a high percentage of second harmonic. Thus, inrush current can be distinguished from fault current. If the current contains a high second harmonic, it is inrush current, and if the second harmonic percentage is low, it is a real fault current. So, when the transformer is started, the relay quickly analyzes the current value resulting from the transformer startup. If this value contains a high second harmonic, over 20% of the set value, it blocks itself from operating. If the second harmonic is below the set value, it allows tripping. During a city power interruption, people often leave devices on. Assuming 50% of AC units stay on, when power returns, all devices start at once, which will result in... When the power goes out in a city, people usually leave electrical appliances such as lighting, television, and refrigerator on by mistake. Assuming 50% of the air conditioning units remained on after the power outage, thus when power returns, these devices start together, causing a high current in feeders. Though significant, this current quickly decreases naturally within seconds, as it mostly represents a high current flows through all feeders, occurring at startup after a long stop. This current decreases quickly within seconds because it mostly represents inrush current. Some overcurrent relays may be affected, thinking it's a fault, and may trip feeders. To solve this, operate on a curve with a long delay for tripping or raise settings temporarily until the current normalizes. After that, the relay reverts to its original curve. This method carries risks, as a real fault could occur at startup without protection. Switch curves using a panel selector switch. After that, the relay returns to its original curve designed for it. This solution is better than other solutions that completely disconnect the overcurrent relay from service until the power returns for several seconds, allowing the inrush current to pass without issues. As we said, this method involves great risks, as a real fault may occur at the beginning of operation without any protection. A questioner may ask, how can I move from one operating curve to another operating curve after a number of seconds? This is done by having a selector switch on the panel. This selector switch is used to select the required curve. This selector switch is connected to the binary input of the relay, allowing you to choose the desired curve by changing the selector switch connected to the binary input on the relay. Through this binary input on the relay, you can select the desired curve. If it's set to 1, it selects the first curve, and if it's set to 0, it selects the second curve. Revival of a nation.